Welcome to the University of Kentucky's Center for Applied Artificial Intelligence. Visit us online at caai.ai.uky.edu to learn more.
Hi, I'm Emily Collier with the Center for Applied Artificial Intelligence at the University of Kentucky. In our first video, we explored what artificial intelligence is, defining it as an umbrella term for powerful tools and technologies. Now, we're going to look inside the umbrella to understand the technological core that makes modern AI systems so capable. In this video, you'll learn about the nested relationship between artificial intelligence, machine learning, and deep learning. We'll show you how this structure represents an evolutionary trend, moving from simple, rule-based systems into the generative AI systems that we see today. While we used to talk about AI in terms of separate branches that worked independently, the field has actually evolved into a nested hierarchy. So think of it less like separate limbs on a tree, but more like a series of Russian nesting dolls, where each layer is a subset of the one before it. The nesting describes the evolution of how machines learn. This is the broadest umbrella and the oldest idea. As an official field, AI dates back to about the late 1950s. For its first few decades, these early systems relied almost entirely on explicit rule-based logic, meaning that a human had to manually code every possible scenario and rule. In practicality, intelligent systems as we know them today were still largely theoretical. Beginning around the 1980s and 90s, however, a revolutionary shift occurred. Machine learning is a subset of artificial intelligence, and it's marked the first major step in the evolution. This technology moved us beyond having to write every single rule, allowing the machine to learn directly from data by discovering its own statistical patterns. These are the core mathematical structures that were developed to make complex machine learning possible. They are multi-layered models, loosely inspired by the human brain, that process information to find intricate patterns. Neural networks were a key development in the history of machine learning. This term represents the modern breakthrough that became prominent around the 2010s. Deep learning is essentially the specialized capability that arises when we use a deep stack of many neural network layers. This depth allows a system to tackle massive, unstructured datasets and solve the complex problems that led directly to generative AI. Therefore, deep learning is the more advanced implementation built from the foundational neural network structure. This newest core is driven by deep learning and highly advanced neural networks. This capability allows a system to create new content, such as text, images, or code, based on the vast understanding of linguistic patterns, context, and raw data. The critical question is, how do these math-based networks actually understand concepts like words or images? This is where the powerful and often overlooked idea of the embedding comes in. Embeddings are the secret language of the neural network. An embedding is the way an AI system converts non-numeric data, like a word or image, or even a clinical symptom, into pure math. It takes concepts into a set of numerical coordinates, otherwise known as a vector, into a massive virtual space. So think of it like a semantic map or a GPS system for ideas. Every word or concept is given a set of coordinates, and the genius is that meaning is represented by distance. Words with similar meanings, like cat and kitten, will have coordinates that place them close together on the map. Words with different meanings, like cat and apple, will be farther apart. And the relationship between concepts is also captured. So the distance between king and man is roughly the same as the distance between queen and woman. So by turning everything into a set of these mathematical coordinates, the neural network can finally do the math on meaning. This ability to calculate relationships and meaning in this embedding space is what unlocks the creative, generative power of modern AI, allowing it to write coherent text, translate languages, and generate new images. So this nested hierarchy, powered by embeddings, shows a clear evolutionary trend in AI capabilities. So in the beginning, we had those rule-based systems. These earliest forms of AI were purely rule-based, explicit if-then code. They were highly specialized, but they were brittle. In the transition period, we have machine learning. Machine learning allowed models to become more flexible by learning statistical patterns from data. And now, in the present, we have deep learning and generative AI. The modern power of deep learning, fueled by neural networks and their ability to map meaning through embeddings, led directly to generative AI. And this is the final stage of our current evolution, where a system doesn't just recognize patterns, but can create new content. So what about the concepts that we used to call branches, like natural language processing, computer vision, or robotics? These fields have been subjects of AI research for decades. and in the past, they were more like distinct separate technologies. So before the deep learning era, natural language processing relied on older statistical methods. Computer vision used unique hand-engineered algorithms to find pattern in images. And these approaches made them feel like isolated branches because they used fundamentally different methodologies. Today, they aren't these separate branches. They are fields of application that are now powered by that deep learning core. So you might say the methodology has merged. Natural language processing uses deep learning and embeddings, often through powerful transformer models, to read, understand, and generate human language. Computer vision uses deep learning and embeddings to perceive, interpret, and act on visual data like images and video. Robotics, sometimes called embodied AI, uses deep learning and embeddings to allow a physical machine to perceive its environment, plan, and execute complex actions. So the true innovation isn't in these fields alone. It's that the same powerful generalized deep learning core, based on the math of embeddings and a unified model architecture, can now be adapted to unlock intelligence across all of them. This is why we now see them as applications of a common core, rather than unique, isolated branches. Knowing the foundations of these areas allows us to better understand what makes up our AI toolkit and what lies under the hood of the concepts that build the AI field. So we've opened up the umbrella of AI to see its evolutionary core. We've learned that artificial intelligence is a nested hierarchy. Artificial intelligence to machine learning to deep learning, and that embeddings are the mathematical language that allows the neural network to understand and generate meaning. This evolution, from simple rules to generative AI, is changing every sector of our lives. In our next video, we'll dive deeper into the single most important input of this entire system: data. Where it comes from, why its quality and diversity are crucial, and how it shapes everything that AI can learn. Thank you.